In this video, we're going to take a look at area between two curves. So here we don't have two curves, we just have one. But let's say this is the function f of x equals x plus 2, and we wanted to find the area under this curve from, say, 0 to 6. So we learned that we could use a rectangle approximation and add up a bunch of rectangles under this curve. And the more rectangles we chose to use, the more accurate our area would be. And then we determined that if we take the integral from 0 to 6 of f of x, that this would indeed give us the area underneath that curve from 0 to 6. And so integrating gives us x squared over 2 plus 2x from 0 to 6 would be 36 squared, 36. 36 divided by 2 is 18 plus 12. And then we would minus, putting 0 in here would just give us 0. So we would get an area of 30 under the curve. Okay, so what if we had two curves? So I've got two curves here, and I've sketched the graph. So f of x equals 1/2 x plus 11, and g of x equals 1/2 x plus 1. And let's say we wanted to find the area between these two curves from 0 to 10. Well, what we could do is we could find the area underneath the black curve. We could do this area all the way underneath this black curve here. And that would give us the area between the x-axis and the black curve. And then we could find the area underneath this red curve from 0 to 10 and subtract them. And then obviously then what we would find would be the area in between the two curves, which is what this question would want. So what would that look like? Well, we would do the integral, in this case, from 0 to 10 of the top function, which in our case is f of x, minus the area beneath the bottom function, which in this case was g of x. And if we did that, that would give us the area between the two curves. So this is our formula here. The area between two curves is equal to the integral from a to b of f of x minus g of x. So the important thing in this formula is f of x. This must be the top function, and this must be the bottom function. Okay, let's look at some examples. Find the area between the curves y equals x squared and y equals negative x plus 6 from 0 to 2. Okay, so what we need to do is consider which one would be our top function. So just a real quick kind of sketch here. Y equals x squared is going to look something like this at 0. Actually, let's make this 1, and we'll make this 2. So 2 would be 4. So the graph's going to look like this. There's y equals x squared. And then this would be a line with a y-intercept of 6, 1, 2, 3, 4, 5, 6, and a slope of negative 1. So let's go down 1, over 1, down 1, over 1. Graph would look something like this. So I made this note that the y-axis went up by 1, the x-axis went up by 2. So I'm only doing this just so that you can see that the top function here is indeed this one, and the bottom function would be this one. And so then finding the area between these two curves, we would say let's integrate this from 0 to 2 of top function, which would be negative x plus 6. Take away the bottom function, which would be x squared. And this will find us the area underneath the top function. And then we're going to take away the area underneath the bottom function to find the area in between the two, which is what the question is asking. Okay, so integrating this, negative x squared over 2, integrating 6 would be 6x, minus integrating x squared would be x cubed over 3, and we're doing this from 0 to 2. So putting 2 into these would give us negative 4 over 2 plus 12 minus, putting in the 2 in the second one here, gives us 2 cubed, which is 8 over 3, minus, then putting 0 in would be 0 plus 0 minus 0, a whole pile of zeros there, which is kind of nice. And we would get negative 2 plus 12 minus 8 thirds. Negative 2 plus 12 is 10. 10 minus 8 thirds would make this 30 thirds minus 8 thirds, getting common denominators, which ends up with an area of 22 thirds. So that would be the area between those two curves from 0 to 2. Let's consider example 2 here. Find the area between the curves y equals x squared and y equals 2x minus x squared. So the problem with this one is we don't actually know the area that's enclosed by them. Whereas this one said, let's find it from 0 to 2. So we're going to have to find out where these two curves intersect each other. So we know that y equals x squared. So I'm going to do substitution here. If y is x squared, I'm just going to substitute my x squared into this function. So that would give me x squared equals 2x minus x squared. Bringing the x squared, adding x squared to both sides gives us 2x squared equals 2x. Setting this equal to 0 gives us this. We can factor out a 2x, which leaves x minus 1. And we got x equals 0 and x equals 1. So these graphs are going to intersect at those 2 points. So now we know it's going to be the integral from 0 to 1. That's where the two graphs intersect. What we still maybe don't know is we don't quite know what the top function is and what the bottom function is. So we could do like a quick little sketch since we're only going from 0 to 1. When x is 0, here is 0, 0, 0, 0 on this function, 0 on this function. When x is 1, this function's 1. And this function is also 1. So our top function is we're going to have to figure this out at a half. A little bit tricky here, this one. So I brought up the calculator here just so that we can see which one would be our top function if we put a half in. So putting a half into the first function produces a quarter. So this graph here, y equals x squared, would be at a quarter, which is about here. So this graph is kind of looking like this. And then this one here, if I put a half in, this would be 2 times a half, which is 1, minus a half squared, which is 3/4. So this one here, when I put 1 in, is going to look like this. So y equals x squared is the one on the bottom, and y equals 2x minus x squared would be the one on the top. So we are integrating, let's move this down. We were integrating from 0 to 1, the top function, 2x minus x squared, minus the bottom function, x squared, with respect to x. So this one was a little bit trickier in that we had to find out where they intersected by substituting the one function into the other to find the intersection points, and then a little bit tricky to know which one was on top. But we determined that by testing a point in between the intersection points. So now we just got to integrate this. So integral of 2x would be x squared minus x cubed over 3 minus x cubed over 3. And we are doing this from 0 to 1. So putting 1 in gives us 1 minus a third minus a third. Minus putting 0 in gives us a whole pile of zeros again. So we have 1 minus 2/3, and 1 take away 2/3 would be 1/3. So area between those two curves is 1/3. Okay, let's look at example 3. So this one here, find the area enclosed by the line y equals x minus 1. And the parabola y squared equals 2x. So the challenge with this one is this one here is going to be difficult to isolate y. If we were trying to isolate y, this would be plus or minus the square root of 2x plus 6. Just show you what in Desmos kind of what these two graphs look like so you can get an idea. So taking a look at this, it's in Desmos, we can see we're going to need to go from -3 all the way up to 5. So that'll be our integral from -3 up to 5. Where this gets a bit tricky is what's the top function and what's the bottom function. So here, let's see what point this is, up to -1. So see, from -3 up to -1, the top function would be this blue graph. Now that's the positive square root of 2x plus 6. And the bottom function would be the negative square root of 2x plus 6. And then after -1, from -1 up to 5, the top function is still the positive root 2x plus 6. And the bottom function becomes this red line, x minus 1. So we would have to do it, we'd have to split it up into two parts. We'd have to go the integral from -3 to -1 of the top function, which was root 2x plus 6, minus the bottom function, which is negative root 2x plus 6 with respect to x, plus then we're going to integrate from -1 to 5. From -1 to 5, our top function is root 2x plus 6, but the bottom function becomes the line x minus 1. So from -1 to 5, we would have to integrate this one, top function, root 2x plus 6, minus bottom function, which is x minus 1 with respect to x. So that's a little bit clunky. That's a lot of integrating to do, a lot of different parts. So another way we can do this that's a lot easier than having to do these two separate integrals with respect to x is, let's go back and look at this graph again. And if we actually look at it this time horizontally, like look at some horizontal bars here, the nice thing about this is your top function would just be this red line, and the bottom function would just be this parabola. So we can actually do this. We can do horizontal rectangles. So that's like integrating with respect to y. And then instead of going from -1 to 5, like we would if we were doing this with respect to x, we would go from -2 to 4, because these are the y values. So let's look at what that would be. Our top function, if we were looking at this with respect to y, would be the red graph. So that's the one x minus 1. And our bottom function would be this whole blue graph, this one here, y squared equals 2x plus 6. The problem is these have been written in terms of y equals. We're going to now have to write this in terms of x equals some function of y. So let's go back and look at this. Let's take this one here. So we had y equals x minus 1. Instead, let's add 1 to both sides. And then we would get x equals y plus 1. So this is going to be our top function. X equals y plus 1. The other function we had was y squared equals 2x plus 6. This one here, if we minus 6 from both sides, gives us y squared minus 6 equals 2x. Dividing by 2 would give us y squared over 2 minus 3. So this would be our bottom function. X equals y squared over 2 minus 3. So now if we're setting up an integral here, and now I can't remember what the y values were, from -2 to 4. So we're integrating with respect to y, so the y values go from -2 up to 4, -2 up to 4. Our top function, which was y plus 1, minus our bottom function, which is y squared over 2 minus 3. And we're doing integrating now with respect to y. Okay, oops. Let's actually do the integrating. So this would become y squared over 2 plus y minus, now we're going to integrate this. So we're going to add 1 to the exponent and divide by the exponent. So that becomes y cubed over 6 minus 3y, and all from minus 2 to 4. Okay, putting the 4 in. So 4 squared, that would become 16 divided by 2 plus 4 minus, putting the 4 in here, would become 64 over 6 minus 3 times 4, which is 12. So there's y, or our function evaluated at 4. Now we're going to put negative 2 in. Negative 2 squared would be 4. 4 divided by 2 would be 2. So that's 2 minus 2 for the first one. Nice 0 happening there. Put in negative 2. Negative 2 cubed is 8. So that'd be 8/6 plus 6. Putting negative 2 in there. Okay, now putting this in the calculator. Okay, so this would be 16 over 2 is 8, so 8 plus 4, that's just 12, minus another bracket, 64/6 minus 12, close, close, minus, well, that's just 0, so minus negative 8/6, whoops, 8/6 plus 6, close, close. Whoops, what just happened there? Close, close. 62/3. So 62/3 would be our area between those two curves there. I think I got that in there right. I might have missed the brackets. There, brackets. 1, 2, that's good. Close, close, open, open. And 8/6 plus 6, close, close, close. Yeah. Good. Yeah, so 62/3 would be the area between those two curves. So just to review, if we want to find the area between the two curves, we integrate from a to b of f of x minus g of x, f of x being our top function minus our bottom function. And if it's easier to integrate with respect to y, then we can isolate y and write y as isolate x and write x as a function of y, and then we can do our top function minus our bottom function, integrating up the y-axis from whatever a to b is.